Okay. I hope everyone's so excited because all of you just gotten back from voting. From voting? Did you cast your vote? No? Yeah. I hope those of you who haven't intend to go and cast your vote. There are a couple of reasons for doing that. Well, you might think that the presidential election doesn't matter because California, anyway is going to go one way, and regardless of what you wish, it's not going to change the outcome. But there are also propositions in California that are quite important, including Prop 30, if you've heard of it. So let me encourage you. Okay. Okay. So let's see. We might discuss later. Well, we won't discuss later, right? I mean, okay. So there are various aspects of elections that are that we can talk about once we know about random variables. But we'll talk about them not today, but in subsequent lectures. Okay. So can people please settle down? Yeah. Okay. All right. So let's remember what a random variable is. It's a function which assigns to each sample point a real number. Okay. So let's do an example. So example is coin tossing. Oops. Okay, so let's say that we're going to toss the coin n times. Each time the probability of heads is p, probability of tails is q, which is 1 minus p. These are independent coin tosses. So we can think for our purposes that n was, say, 5, but that's for the purpose of the example, but actually n is very large. N might be something like what we have for the elections today, which is, and face it, it's like coin tosses, right? I mean, 50-50, that's what it seems to be. And okay, so N is like, what would you guess it is? Is it around 100 million or maybe 80 million? How many people vote? It's some large number. N is large. Okay, now, X, which is the random variable we are interested in, is the number of heads. Okay. Now, okay, so what do we mean by a random variable? So we perform the experiment. What happens when we perform the experiment? So we perform the experiment. And what we get is a sample point. Which we'll call little omega, which might be something like heads, tails, heads, heads. Okay? And now our random variable is a function from the sample space to, well, if it's an integer random variable, then it's a function from sample space to integers. So x we can also write as x of omega, which we usually suppress, right? Because we don't want to think too much about it. But actually, it's a function. So it's a function of the sample point. So what is x of omega in this case? So you perform the experiment and you see how many heads came up. So it's 3. Okay, but now, this is not enough for us because, we started thinking about random variables And now suddenly we want to think about many more random variables. Okay, so which other random variable can we think of here? So how about x1, which tells us, which is 1 if the first toss results in heads and 0 otherwise. Otherwise, meaning if the first toss is a tails. Okay? And actually, while we're at it, why don't we let x sub I for I equal to 1 through 5 be similarly defined. 1 if the ith toss is a heads. Okay? So now, of course, x sub I is also a function of omega. Right? We are performing an experiment. We toss the coin 5 times. It comes up, maybe this is still the outcome. So the outcome was heads, tails, tails, heads, heads. And now, we can look at any random variable we want, and we can figure out what's its value. So what's the value of x1? x1 is 1. x2, x3, x4, x5. Okay, now x happens to be the sum of x1 plus x2 plus x3 plus x4 plus x5. Right? Will that always be true? Right? So remember, x is a function. It's a function of omega. We are saying x is equal to x1 plus x2 plus x3 plus x4 plus x5. Right? What we mean by this is that x of omega equal to x1 of omega plus x2 of omega plus x3 of omega plus x5 of omega. Right? So no matter which sample point you draw, x happens to be equal to x of omega is equal to x1 of omega plus x2 of omega plus so on. Does that make sense? Okay. Okay, this is called the binomial distribution. Right? When you toss a coin n times, bias coin n times, and you want to know how many heads, it's a binomial distribution. Okay, so how do you represent a distribution? So here's what we mean by representing the distribution. So, we have a random variable x. Okay? To talk about the distribution of x, we say, well, what are all the values that x can take on? Well, x takes on the value little a, where a ranges over some set capital A, right? So if it's an integer random variable, the set, script A would be the integers, and little a would be a particular integer, right? So you'd say, what's the probability that x equal to 3? Well, what's the chance that you had 3 heads in this particular experiment? So when we say the distribution of a random variable, what we mean is, what are all the possible values it can take on, and for each value, what's its probability? So for example, this might be the probability distribution when you toss a coin 9 times, and let's say the probability of heads was a half. Right? So the chance that you get 0 heads is something for 1, 2, 3, 4, 5, etc. And this is called the binomial distribution. Right? This is another example of a binomial distribution where n is larger, p is small. Okay, and you say, what's the probability of 0, 1, 2, etc. And now you see this curve is shifted over towards the left because p is small, n is pretty large, right? Okay. Okay, so you get this bell-shaped curve in either case, okay, closer and closer to a bell-shaped curve as you let n get larger and larger, but this is the probability distribution. Yeah, does this make sense? So these concepts are not that difficult, but there are a few different ones, and it's important that you latch onto them and they make sense to you, right? If they make intuitive sense to you, what comes later is just going to be, well, piece of cake, maybe, but well, almost a piece of cake. Okay, it's some form of dessert. Okay, but what you don't want to do is to go into the rest of what we are going to get into, sort of thinking to yourself, yeah, what was a distribution? Let's see, a random variable, wasn't it a function? I don't really quite know what it was, right? So you should be somewhat more fluent with this. It should be, so remember, there's this intuitive notion, you're performing an experiment, right? When you perform the experiment, you get, as a result of the experiment, you get a sample point. And now, looking at that sample point, you figure out what your random variable is, right? So your random variable, what you wanted was the number of heads, so you read off the number of heads, right? You read off the value of this random variable from the result of your experiment. That's what you do, okay? All right, so now, oops. Okay, so let's move on to talking about this example that we had the last time. So we'll, just to get another type of example. So remember we had this example where, I don't know what we said, what the story was. Maybe the story was there was a little bit of a snafu in handing back homeworks. The grader was it was over Halloween weekend. There were too many parties to go to. And everything got a little bit messed up, and he was just rushing out of the door when he realized he had to enter the homework grades, and he thought, "What the hell? Let me just do them at random. Hopefully, it'll all turn out right." And okay, so so you had your n homework n students, n grades, and everything got permuted at random, and we want to know how many people got the grades that their own grades, right? So here was an example with n equal to 3, and so each possible, so 1, 2, 3 is the correct order in which the grade should have been entered, and then the x, our random variable, is the number of students who got the correct their right grade. So x would be 3, 1, 3, 2, and now only the first student got the correct grade, and so on. Okay, so that's another. Okay, so these are our sample points. That's the value of the random variable on this sample point. Okay. Right. Just belaboring the point a little bit. So sorry, I'm belaboring the point so that when we go forward. You still have a picture of what's going on, which is going to be quite important. So remember what we are saying is, this is our model of what the probability distribution is, right? There are these different values that the random variable can take on. For each one, we have a probability, right? And how did we get this probability? We said, well, look, you had your random variable where it's a function on the sample space, so that's our sample space. Right, you have sample points all over here, and then there are those sample points where the value of the random variable is A3. That's this region of the sample space. There's a region where it's A1, there's a region where it's A2, right? So each of, the x equal to A1 is an event. It's a subset of the sample space, right? And then the probability x equal to A1 is exactly what we plot out there. Okay. So in our particular example, those are the probabilities. Okay. So this is just reading off the case, of the returned homeworks with 3 of them. Okay. So now, here's the point about probability distributions. So in general, as n gets large, and as the so we'll look at random variables which get pretty complicated. And so figuring out what the probability distribution looks like is going to be an extremely challenging problem. Okay? So figuring out what's the probability that x equal to I is going to be, it's going to get more and more difficult to do. And so what we'll try to do is we'll try to, we'll try to work out some statistics related to this probability distribution, which are useful for us to figure out roughly what's going on. Okay? These statistics are things like expectation or mean, variance, standard deviation, things like that. And so what we'll try to do in general is we won't be able to figure out what this distribution looks like. We won't be able to plot it because it's too difficult to do. But we'll be able to understand the shape of the distribution by understanding a few parameters about this distribution. And that's where we're going to next, is figuring out what these parameters should be. Okay, so here's the first parameter we are interested in. It's called the expectation of the probability distribution. It's the expectation of the random variable. So the expected value of a random variable x is by definition the sum of a times probability x equal to a. Okay? So let me think of this as an integer random variable. You can think of it as an integer random variable, right? So a belongs to the integers, right? So your random variable takes on only integer values, and now the expected value of x is just the sum over all integers a of a times the probability x equal to a. Okay? So for example, if you're rolling dice, right? You roll a die, and now you want to know what's the expected outcome. So if x is our random variable, which says what's the outcome, what's the expected value of x? Right? So it's 1 times 1 over 6 plus 2 times 1 over 6 plus so on up to 6 times 1 over 6. Right? Which is 6 times 7 over 2. Is that what it is? Times 1 over 6. Right? The sum of the numbers 1 through n is n times n plus 1 over 2. So that's 7 over 2, which is 3.5. So that's the expected roll of a die. Right? Now, of course, if I define for you another random variable, which was, so suppose I define for you another random variable y, which takes on the value 3.5, no matter what the outcome of the die is. Right? So here's another random variable y. Okay? It's perfectly fine for you to say this is a random variable. What you do is you roll a die. It's a fair die. You look at what comes up, and then you say the value of this random variable is 3.5. Okay? Does everyone agree that's a random variable? So is this a random variable? Okay, so this is x of omega. This is y of omega. Is that a random variable? It's a function from the outcome of the roll of from this sample space to, well, it's not an integer random variable, but okay, well, it's a discrete random variable, right? So is everyone okay with the fact that it's a random variable? Now, what's the expected value of y? It's 3.5, right? So remember, when we are talking about the expected value of a random variable, it's just a statistic. There are different distributions which will have the same expected value. And they may look quite different from each other, right? But what we are saying is, if you didn't want to know all the details of the random variable, of the distribution of the random variable, maybe this is, and if somebody told you, I'll tell you one number about the random variable, whatever you want. Maybe this is the right number you want to know. Because to a first approximation, maybe you should think that x is more or less like this one, like y. Okay, does that make sense? Yeah? And then what we'll do is we'll come up with more and more parameters which will allow us to understand this probability distribution better and better. Yes?
What's the difference between the expected value and then the most likely value?
Oh, good. Very good point. Okay, so let's see. What's the difference between expected value and most likely value? So suppose that you're flipping a coin, right? So you're flipping a coin. Say probability of heads is 0.9, probability of tails is 0.1. X counts the number of heads in one toss. So X is 1 if heads, 0 if tails. Okay, so this is our random variable. What's the most likely value of X? What's the expected value of X? Yeah, so it's 1 times 0.9 plus 0 times 0.1. So it's just 0.9. Right, so the expected value doesn't have to occur at all. Right, so the expected value of X may never occur. But it sort of tells you, this is where, this, in terms of the distribution, it tells you something. So what does it tell you about the distribution? Here's what it tells you about the distribution. Okay, so if you think of this as the probability distribution, right? That's, this is what, this is A. That's the probability X equal to A, right? So now imagine taking this probability distribution and making a wood cutout, which looks like that. So you make a certain shape, a physical shape that looks like that. And now you ask, what's the center of gravity? Where does the center of gravity of this shape lie? Right? Where would it balance? And the answer is, that's exactly the expected value. Okay? So the sense in which the expectation is a good statistic to know about probability distributions is the same sense in which when you have a physical object, it's good to know about its center of gravity. When you're looking at it from a distance, you may as well think of the entire mass being concentrated at the center of gravity. And that's the same thing here. Right? So looking at it from a distance, you want to think about this as the typical value of the random variable. Okay, and we'll make this, so one of the goals of probability theory is to make this precise. In what sense you may as well forget about the probability distribution and think only about the expected value. In which conditions can you do this? Right? That's really one of the big goals in probability theory, and we'll sort of talk about that in this next lecture or two. Okay, does this make sense? Okay, so what we want to say is, if you draw a number of samples from this probability distribution, and if you take the average of those samples, then that average is going to be very close to this expected value. Right? That's the whole point about expected value, and that's why it's an interesting thing to study. Okay, so maybe it's time for a quick break, and then Okay. Okay, now, one of the reasons that the expected value is so useful is because it's very easy to calculate. Okay, and what makes it very easy to calculate is this fact that if you have any two random variables, x and y, on the same probability space, then the expected value of x plus y is the same thing as the expected value of x plus the expected value of y. Okay, this is an extremely powerful theorem. It's an extremely powerful fact. And it's one that's going to, if you're calculating expectations, it just simplifies your task tremendously. So let's do some examples of this. So what do we mean by x and y are on the same sample space? So let's remember the example from earlier when we were tossing a coin 5 times. So we had probability of heads equal to p, probability of tails equal to 1 minus p equal to q. And then we said we tossed it n equal to 5 times, and we said x equal to number of heads in the 5 times. And then we defined x1, x2 through x5. And we said x actually equal to x1 plus x5. Okay. So now suppose that we wanted to compute expected value of x. Right? So if we do it by definition, then this would be 0 times the probability that x equal to 0 plus 1 times the probability x equal to 1 plus so on up to 5 times the probability x equal to 5. Right? And what would this value be? Well, it would be 0 times, what's the probability x equal to 1? So x equal to 0 means that you have no heads at all. You toss the coin 5 times. So that's q to the 5 plus 1 times probability x equal to 1. What's the chance that x equal to 1? So it's any sequence where there's exactly 1 heads. Right? So how many such sequences are there? 5 choose 1. And then the probability of any of them is p times q to the 4th plus 2 times 5 choose 2 times p squared times q to the 3 plus so on. Okay? So as you can see, this is, it takes a bit of doing to figure this out. Right? But now you could also use linearity of expectations. And you could just say expected value of x equal to expected value of x1 plus expected value of x2 plus so on up to expected value of x5. Right? Because x equal to x1 plus x2 up to x5, we know, if you add random variables, the expectation just adds. Right? So it's just the sum of the random variables. Now, what's the expected value of xi? Well, first of all, these are flips of the same coin, so all these expectations are the same. So you may as well say this is 5 times the expected value of x1. Right? I mean, that's clear, right? It's 5 times the expected value of x1. But what's the expected value of x1? Well, it's 1, so x1 is 1 with probability p, 0 with probability 1 minus p, so it's 5 times 1 times p plus 0 times 1 minus p, which is just p. So that's what it is. That's the expected value. It's 5p. Right? Okay, so you haven't even seen the half of it, right? I mean, this is an incredibly powerful fact about expectations. By the way, while we are doing it, is everyone happy with this? Should I keep going? Anyone want to keep staring at this for a few more seconds? Yes. Okay, well, so E is expectation of x1, right? There's an expected value of x1, expected value of x2, and so on. What's the expected value of x1 mean? Meaning that the first time you toss a coin, so let's go back. Remember what our, okay, so let me go back to the basics. What's our experiment here? We toss a coin 5 times. So we do this experiment. So we have a sample point omega, right? What's the sample point? Well, it might be tails, tails, heads, tails, tails. Right? That's what may have come up. It's whatever came up, right? What could I do? I tossed the coin. This is what came up, right? Okay. So now, what's x in this case? It's 1. What's x1? It's 0, right? Because it was x1 says, did the first one come up heads? x2 is 0, x3 is 1, x4 is 0, x5 is 0. Okay. But now we could also ask, what was the expected value of x1? X1 happened to be 0 this time. But remember, we tossed a coin, right? It need not have come up 0. It had some expected value. What was the expected value? Right? It's 0 with some probability, 1 with some probability. So we want to find the balance point, right? So we say it's 0 times the probability it's 0 plus 1 times the probability it's 1. So what was the probability it's 1? It's p. Right? What about the second coin flip? What was the expected value? Well, it was the same coin, right? We tossed it again. What's the expected value? It's the same value, right? So we could have done this calculation 5 times and said each time we flip the coin, its expected value was p. But instead, we can also short circuit that process and say, well, it's the same coin we are tossing. The expected value of one coin toss is always the same, right? The expectation is the same, yes? Okay? Okay, so, well, let's continue with this. So now let n be n. So we are tossing a coin n times, right? So probability of heads is p. We toss n times. Probability of tails is q. So now what's the expected value? X is number of heads. Right? This is called the binomial distribution, by the way. What's the expected value? Well, it's sum k equal to 0 to n of k times the probability x equal to k. Which is what? Which is summation k equal to 0 to n, k times, what's the probability x equal to k? Well, if you're going to have exactly k heads in n tosses, well, there are n choose k ways of picking where those k heads occur. And then for each of these sequences, the probability is exactly what? Well, you fill in heads in all those k spots. The chance that happens is p to the k. The chance that all the other spots are tails is q to the n minus k. So that's what it is, right? But on the other hand, you can also evaluate the expectation of x by saying x was x1 plus x2 plus xn, where xi just says it's 1 if the ith coin flip was a heads. And so now, by the linearity of expectations, this is expectation of x1 plus expectation of x2 plus so on up to expectation of xn. Right? By the way, how did I get from here to here? All I told you was if you had two random variables, x and y, then the expected value of x plus y is expected value of x plus expected value of y. How did I get it for three random variables and 4 and 5? Induction. Oh, great. Okay. So, yeah, and at this point, we don't go through induction proofs, right? We just say induction. And yeah? Okay. So okay. So now what do we do? Well, now we just say each of these expectations is the same. And how much is each of these expectations? What's the expected value of xi? It's exactly p. So you get n times p. Okay. So what can you conclude from this? There's something you can conclude. Actually, maybe there are many things you can conclude, but there's a mathematical fact you can conclude from this. Yeah, you can say that expression, that summation, that ugly-looking expression, that horrible-looking expression, it evaluates to n times p. Right? So imagine that somebody told you, evaluate for me this expression. And you were thinking, I have no idea how to even get started. Right? Well then, and then it occurred to you, actually that expression, what it is it's exactly the expected number of heads when I toss a bias coin n times. Okay? And then you could, once you realize that, you're home free, because then you could say, well, expectations, I know how to compute them. Linearity of expectations, it's exactly this. Okay, so let's do another example. For this example, you have to suspend your skepticism for a few minutes. Okay, because in this example, we are no longer going to be dealing with discrete random variables, it's continuous random variables. So what does it mean? Well, it just means what it seems like intuitively, and we are not going to get into what it really means, but we are just going to use our intuition and get through this example. Okay? You could sort of, the example would make sense in a discrete case, but then it gets a little more complex and it gets a little more complicated, and I don't want to deal with those complications right now, so I'll just imagine that, and it's most natural to do it in a continuous setting. So here's the setting. This is sort of a, it's sort of, what's it? This is a game of darts, the way, how many of you see The Big Bang on TV? Yeah? Yeah? Okay. So is it, I'm sorry? Sorry? Oh, Big Bang Theory, yeah, right, Big Bang Theory. Right, you're right. So, this is sort of like, so imagine that Sheldon and company went to a bar and they were playing darts. Okay, but this is sort of, it's like darts for geeks, right? So instead of having the usual dartboard, now your dartboard is a line. Okay, it's a line segment between 0 and 1. And since these guys are not very coordinated, the objective of the game is not even to hit a particular point, because it's pointless. Okay, so what they're doing is they just throw darts at random on this line. Okay, so each of them throws a dart, and it goes somewhere. So let's say that they throw k darts. And now what you want to know is, how long is this how close do they get to the left endpoint? What's the expected length of that first interval? Okay. So you're assuming the dots are sort of landing uniformly on that unit interval. You throw k of them. They land uniformly. Maybe the objective of the game was to get as close to the left endpoint as possible, but these guys, they just, it was just everywhere, right? So each dot landed uniformly on the unit interval, but we want to know the person who won, right? How close was that first dot? What's the expected length of this interval? So if we call this interval x, we want to know what's the expected value of x. Yeah? Okay. So now, so we are doing this example just to illustrate the linearity of, the power of this concept of linearity of expectations. If you try to write out this expression, assuming you've, worked through whatever continuous probability means and, probability density functions and so on, you get some awful mess there, right? You can write out the expected value, and now instead of a summation, it'll be an integral of something, and it's not an integral you really want to evaluate. So how do we figure out this expected value without doing any integrals? Okay. So here's the idea. Oh, actually, do you want to think about it for a minute? Okay. Is anyone ready for a hint? Yeah. I'm sorry? No? Anybody want a hint, or anybody ready to answer it? Or? I'm sorry, you want a hint? Okay. I'm sorry? I'm sorry? Is it what? Oh, this is a continuous, because these points can land at any real value between 0 and 1, right? So we have a unit interval, and the dot can land anywhere. I'm sorry? Independent of the number of points. So I'm not looking at a particular dot. Now we have thrown k dots, and I'm looking at the leftmost one. Is it half? So no, that's not the. Okay, so let me give you a hint. Okay, so instead of calling this x, okay, here the hint is, let's call it x1. Oh no, okay, maybe a little more of a hint. Okay. Okay, and let's call this one x2. And let's call this one xk or xk plus 1? Xk plus 1. Right? Okay. And now, can you show that the expected value of xi is the same as the expected value of xj? For all I and j. That they are all the same. What would it take to show that all these So by the way, suppose that the expected value of xi was the same for all I. Then can you solve the problem? Okay, so maybe let me give it. Okay, so let me assure you that the expected value of all these xi's is the same. Now, can you figure out what the expected value of x1 is? So is that, how many of you see how to do it under that assumption? Okay. Maybe take a minute to think about it, the rest of you, right? Okay. Okay. So let's go over it slowly, right? So just so that it's clear what what we are dealing with here. So what's a sample point going to be here? So we are doing this experiment, right? Everybody throws a dart, and then the outcome is what? Where the darts land, right? For our purpose, it doesn't matter in which order they land because all we care about is the relative spacing. So for our purpose, the sample point is something like this. It's the location of the k darts in order, right? So it might be, it might be 0.2, 0.35, 0.6. 0.81, right? Maybe there were 4 of them, and those are the locations of the 4, right? Now, given that this is the case, what's x1 of omega? It's 0.2. What's x2 of omega? 0.15. So it's this minus that. x3 of omega. It's 0.6 minus 0.35, it's 0.25. x4 of omega is 0.21. And x5 of omega is 0.19. Right? What happens if you add up x1, and x1, x2, x3, x4, and x5? Right? So it's 1. Now, is that a coincidence? No, right? Because it's by design. So we can say that x1 plus x2 plus so on, xk plus 1 is always 1. Right? Yes? Do you mind if I call this a random variable y, which is always 1? Yeah, no? It doesn't matter. It's okay. We don't have to do that. Okay, so now we can use linearity of expectations. Expected value of x1 plus x2 plus xk plus 1. What is that? It's 1. Right? It's 1 because it's always 1. Right? But it's also equal to expected value of x1 plus expected value of x2 plus expected value of xk plus 1. But remember, we made the assumption that all these expected values are equal. So it's just k plus 1 times the expected value of x1. So the expected value of x1 is 1 over k plus 1. Right? The more darts you throw, the closer the leftmost one is to the left endpoint. Makes sense, right? Because you expect them to spread out sort of evenly. Yeah? Does it make sense? Does the answer make sense? Okay, so I'm sorry? Okay, it's 1 over k plus... Okay, so remember we said x1 plus x2 plus xk plus 1, it's a random variable. It always takes on the value 1. Right? But the expected value is also, by linearity of expectations, expected value of x1 plus expected value of x2 plus expected value of xk plus 1. But now we are still working under the assumption that all these intervals are equidistributed, that they have the same expected value. And so it's just k plus 1 times the expected value of any one of them. So say x1. And so the expected value of x1 is 1 divided by k plus 1. Yeah? Okay, so now, how do we know that the expected value of x1 is the same as the expected value of x2 is the same as the expected value of xk plus 1? How do we know all these expected values are equal? Well, you might say that, well, there's no reason one of them should be smaller than the other. But in fact, there's a reason because, some of them are closer to the edges, some of them are far from the edges. How do we know? Right? Maybe the one that's closest to the edge should be the smallest. Or maybe it's largest, right? Because it's hard to hit close to the edges. How do you know that it's not hard to hit close to an edge? Yeah. Oh, fantastic. Yeah. Well, that's very good. Okay. So that's a brilliant idea. So what you do is, okay, so you first realize that it's Sheldon and company. They'll hit randomly no matter what the shape is. Okay, so they're equally bad at hitting a straight line as they are at a circle. So what you do is, before you start the game, you take the circle. Sorry, you take the line segment and you wrap it around to make it into a circle. Okay? Except it's not quite a circle, right? Because it's a circle with one identified point, which is the point where 0 meets 1 when you wrap it around. Right? So you get this kind of a, this is 0, this is our, oh, okay, sorry. You get a circle, but then there's the point at which we folded everything together, where we stitched it together. And this was 0/1, right? Okay. Now, of course, where that one point is located doesn't make any difference. So let's call that the first dart. And where it fell makes no difference at all because it was, after all, it was a circle. If you start with a circle without any darts and you throw one dart at it, you can call that this first point. So now our experiment is the same as starting with a completely unmarked circle and throwing k plus 1 darts at it, right? Where one of them is our special one, right? And then we look at one of the intervals. So we are throwing k plus 1 darts at the circle, and we want to know what's the expected length of some interval, right? But now it's a completely symmetrical problem. All these intervals are, by symmetry, they have the same probability distribution. And therefore, they have the same expected value, expected length, right? Just by symmetry. And so we know that all these x sub i's have the same expected value. And so we are done. Okay, is that convincing? Okay, yes.
So the question in the beginning was to see what the expected distance between any given dart and the starting point was.
Between the closest one.
The closest. And then that expected distance was 1. So,
What was?
because when we calculated the expected value, that ended up being 1.
No, that ended up being, sorry. Okay, let me do the last step. The last step was, therefore, expected value of x1 equal to 1 over k plus 1.
Okay, now I'm missing.
Yeah. Yeah. So you don't see why we had to do this wrapping around into a circle? See, we wanted to say that the expected value of all these intervals is the same. But when you have them sitting on the unit segment, there's no symmetry to tell us that they are all the same. Because just imagine you're throwing darts at this segment. How do you know that it's not harder to get close to one of the endpoints? Maybe the darts all bunch towards the middle. How do you know? How do you know that the length of the interval from the leftmost endpoint to the first dart doesn't tend to be a little longer than the middle, right? It could be. I mean, there's something special about the left endpoint and the right endpoint there. Okay. And yes.
Can you make an assumption that unit cost of the cross will be a straight line?
I'm sorry?
You're making the assumption that cost of dots to a straight line should be equal to unit cost of dots to the circle. How can you be sure they're the same? I mean,
Oh. Oh, I see. Well, no. So what I'm saying is, we just bent it into a circle, right? So we took this line. So we are doing two experiments. One, we let them throw the darts, and then we bend the line into a circle, right? And then we are saying, actually, the process is the same. What we'll find there is the same as though we started the process from scratch and had the circle, and then had them throw darts at the circle at random, right? Because if each dart falls at a random point along the line segment, then if you measure its distance from a given point on the circle, that's also, it should also be random. So once you wrap it around, and so it's the same process. Yeah? Okay, so here are a couple of challenge problems, assuming you understood this. Okay? So the first problem is, So we are in the same process, except now instead of this first interval, what we do is actually one of the characters, walked up to the line and pointed at a random point. Okay, so they sort of picked a random point to point at and said, I don't believe that a random interval should have length 1 over k plus 1. And so what they did was they pointed at a random point on the line, on the segment, and looked at the length of the interval that their finger fell in. They said, it doesn't look like 1 over k plus 1 to me. So should this person have expected the length of that interval to be 1 over k plus 1? So not the leftmost one. Now this person is sort of saying, let me pick an interval at random. I'll point at a random point and see which interval it fell into, and I'll measure the length of that interval. Okay? So what's the expected length of that interval? Okay, so point at random interval. Okay, meaning you pick a i. So by picking a random point, what's the expected length of this interval? Okay, so that's one question. I claim you can solve this also by similar kinds of arguments. Okay, the second question, that's question number 1. The second question is, it sounds, when you first look at it, it sounds very complicated. But the claim is you can solve it by similar methods. And again, it's linearity of expectations, okay, which is, it's just extremely powerful. So this this particular problem is it has a name to it. It's called Buffon's needle. Well, the way it works is, let's imagine that our plane has been ruled with these lines which go out infinitely, and they are unit distance apart. Okay, so the distance between the lines is 1. And now you take a needle, which is of length 1. Okay, so this is the floor. You take a needle of length 1 and you drop it at random on the floor. So dropping it at random means that it rotates at random and it falls at a random point. Okay, so it falls somehow, maybe it's of length 1, maybe it falls like that. So it's in a random orientation and a random, so it's randomly rotated and it's at a random point. Now what you want to know is, what's the probability? So you want to know, what's the probability that the needle crosses some line? Okay, so in this case, it did not cross any line. We want to know what's the probability it crosses some line. Okay? This is actually very challenging. So, do it only if you have, if you are looking for something interesting to do. Okay, let me put it in a different way. If you think about it and if you don't solve it, there's no reason you should feel bad about it. Okay? If you think about it and you do figure out a way to make progress on it, you should feel very happy about it. Okay, so just to put it in perspective, yeah.
Is it equally likely to hit any line?
Let's say that we are just dropping it randomly anywhere. Yeah. It sort of doesn't matter. You could imagine that this was all happening on a, it was all wrapped around. It was on a cylinder. and that you drop, so you don't have to deal with the fact that it's infinitely large or anything. Just assume locally it's random, and that's good enough. Okay. Okay, so let's do one more example before we run out of time. Let me just go back to an example that we already looked at. So in the case of these randomly distributed homeworks, we could ask, what's the expected value of x? So remember what x was? X was the number of people who got back their own homeworks. So in this case, it is, we can do it by definition. It's all these 6 cases are equally likely. So it's 3 times 1 over 6 plus 1 times 3 over 6. Right? Those are the only cases, plus 0 times whatever, 2 over 6, which is 3 over 2, which is half plus half, which is 1. Okay? So now, let's try to solve the same problem, but with n homeworks and n students. Right? So we have n students and homeworks. They are returned at random. We want to know x is the number of, let's just call them fixed points, meaning that homework I went to student I, right? And okay, so let's let xi be a random variable, which is 1 if homework I returned to student I, and 0 otherwise. So now x is equal to what? x1 plus x2 plus x sub n. Right? The number of people who got back their own homeworks is exactly the sum of x sub I, because x sub I is 1 if the ith person got back their own homework. Right? Now, what's the expected value of x sub I? What's the chance that the ith student got back their own homework? It's 1 over n. Right? Does everyone see this? Okay, so where did the ith homework go to? It went to a random person. What's the chance it went to the ith person? 1 over n. Okay, so linearity of expectations, expected value of x is summation expected value of x sub I equal to 1 through n, which is just n times 1 over n. So it's 1. Yeah?
Isn't that, I feel like that's not right, because...
Yeah, isn't it? It's really not, but yeah, tell me more.
Well, that's it's only 1 over n for the first one, and then it's 1 over n minus 1, the chance that it goes.
Oh yeah, but remember, what we are doing is, what's the expected value of x sub I? It's just, we are performing an experiment, right? So what do? We take the homeworks, randomly distribute them back. Okay? So, and then what do you get as a result? You get a sample point. You draw a sample point. Right? And you look at that sample point, and from that you can read off the values of x1, x2, x3, and so on. And of x. That's all something you can do. But now suppose that you're only interested in x sub I. Right? You don't care about what happens anywhere else. That's the only thing you care about. So you draw your sample point and you only look at x sub I. You look at whether the ith, in fact, you're the ith student, right? So you don't care who else got back their homework. You care whether you got back your own homework. Okay. So what's the experiment from your point of view? From your point of view, what happened is, this grader reached in at random, handed you back a random homework. Okay, let's not talk about him, but what's the chance you got back your homework? 1 over n. There you go. So what's the expected value of your random variable, which x sub I is 1 over n? Okay. Now we don't care about whether, these x sub i's are highly correlated. If you happen to know that x1 equal to 1 and x2 equal to 1 and x sub n minus 1 equal to 1, and you're the last person and everybody else got back their homeworks, now what's your chance of getting back your homework? It's 1, right? Because there's nothing else that can come back to you. So it's 1. But that's after looking at the rest. It's conditioned on the rest. But if you don't look at the rest, then you know that your chance of getting yours back is 1 over n. And so the expected value of xi is 1. But that's true for every person individually. And that's what linearity of expectation says.